Thanks for the kind introduction. Also a warm welcome from my side. So imagine we could use non-recyclable waste and produce electricity and heat out of that, and that with a high electric efficiency. And I say, yes, we can. Is this presentation working? Yeah. So we use a solid oxide fuel cell system which we fuel with landfill gas. And this is my topic for the next 10 minutes. So, that is not working at all. So, yeah, so I will continue with motivation, coming to some challenges, then some investigation at cell level we carried out at DTU Energy, and then I will give a conclusion about what we can learn from our investigation at cell level for our system level. So, starting with the motivation. What exactly is landfill gas? Landfill gas is evolved by non-aerobic digestion from non-recyclable waste and consists basically out of methane, carbon dioxide, nitrogen, and impurities like sulfur and siloxanes. And the normal way is to use a combustion engine to convert that in electricity and heat. But there we have the disadvantage that we cannot use landfill gas with a low heating value, means with a low methane content. And also we have a lower electric efficiency. And there is where I say we can use a solid oxide fuel cell instead, where we produce a high electric efficiency we have, so we produce more electricity, and we can also use landfill gas, which we cannot use in a combustion engine anymore. And that is the interesting part for our partners, which are located in Odense in the middle of Denmark. They're running this landfill site, and here you can see a picture with the gas extraction unit. And they have a gas composition of around 34% of methane, so the methane content is already today quite low, and also 23% of carbon dioxide and a little bit of oxygen and 42% of nitrogen. And this methane content is declining over time. So at one point, they will not be able to use this combustion engine anymore they're running nowadays. And that's the reason why we are looking into it from DTU Energy, and furthermore, they would like to reduce emissions, and there also solid oxide fuel cell can help. So, coming now to some challenges we have to consider if we want to run this kind of system. So, what do we need to consider? The normal way would be if we run just a solid oxide fuel cell, we would operate with hydrogen, put air, oxygen on the cathode side, we produce electricity, heat, and we have steam as the exhaust. Now we have the advantage of the solid oxide fuel cell to use also carbon-containing fuels like methane. So if we would do it directly, we would can use the nickel phase, which is present at the anode, to do internal reformation of methane into hydrogen. If we just fuel pure methane, then we would produce hydrogen, but we would also produce carbon, and that is not good. So we don't want to have this. So we need to have a reforming agent to prevent this carbon formation. And there we have two options. One is steam reforming, where we just use steam, and the other one is dry reforming, where we use carbon dioxide. So coming from the carbon-containing fuels now to the landfill gas. So what do we have there? And there, if we have a look, we can see that we have methane, and then we have also a certain amount of carbon dioxide already present. Means we can use this carbon dioxide already to reformate our methane. This is quite nice. So we do not need extra. But for the beginning, we need to have some extra gas supply, because this amount of carbon dioxide is not enough. So, but we would like to get rid of this amount extra gas supply, because that is not really nice during our operation system. So if we have a look on the exhaust, we also see that we have steam and carbon dioxide present there. So why not, during operation, do a little bit of recirculation of the anode exhaust gas back to the inlet and have enough reforming agent in terms of carbon dioxide and steam present to reform our methane. And that is what we looked into, and this is, I will spend now the second part of my presentation about some investigations at cell level to look on this kind of anode fuel recirculation to prevent carbon formation of a landfill gas fueled solid oxide fuel cell. And there we just divided our setup into two parts. So the first part is a simulation part, where we implemented a model in Python, a semi-1D cell model. Yeah, and there you have just our cell, and this is divided in n subcells. We have our landfill gas coming in, our extra CO2, our anode exhaust gas, and then we have our fuel recirculation, so we can variate these parameters. And then we have the aim to find suitable operation conditions for landfill gas fueled solid oxide fuel cells using anode fuel recirculation to prevent carbon formation and make that available. So going a little bit more into detail, so the most important parameters are our landfill gas composition, our fuel utilization we want to operate the system with, the current density, the extra CO2 we apply, the recirculation rate, and the model was based on Gibbs-free energy minimization, so we are looking from a thermodynamic point of view on this problem, then Faraday's law, that are the two most parts. Then the output parameters are gas composition of each subcell, carbon activity of each subcell, which is an indication for carbon formation. And going more into detail with this, coming to the first results. So the highest carbon activity we can see at the cell inlet. So that you see here. So on the x-axis we have the cell inlet here and the cell outlet here and the carbon activity here. So everything above 1 would mean from thermodynamic point of view carbon formation. With this operation parameters we have, so running at 750 degrees, fueling with landfill gas, applying 0.5 amps per square centimeter, we would be in a safe range from 50% even down to 10% fuel recirculation. So we do not really need to recirculate a lot to be safe. And this is quite nice. Furthermore, we can say to avoid carbon formation, we need to have the recirculation rate proportional to the methane content present in the landfill gas, the fuel utilization, and also the applied current density. And from theoretical point of view, we would be also able to have an increase of electric efficiency by 4 to 5% if we run with fuel recirculation. So, keeping that in mind, we started the second study, the second part, and this is a single cell test. We conducted that at our standard single cell test we have at DTU Energy for solid oxide fuel cells. We modified this rig a little bit, so we added an option to use real landfill gas we got from our partner to the anode supply, gas supply. Then we also added a pump to be able to do the recirculation. Our cell is placed in a furnace which was operated at 750 degrees, and there in the cell house. And the cell is a standard in-house produced cell from DTU Energy, state of the art, with an active area of 16 square centimeter. We have also here again a current density applied of 0.5 amps per square centimeter. Anode supply is landfill gas pre-mixed. So first of all we tried with a pre-mixed version, and then we used the real from our partner. Also extra CO2 could be applied, or fuel recirculation. The cathode was applied again with air to keep it simple. Yes, so what could we get out of this? So having here on the bottom the x-axis the time, so that is 150 hours we were operating this single cell. On the y-axis you see the power density, and the black curve is representing the reference case. So then we were running with premixed biogas, and we used extra CO2 all the time for the carbon to avoid carbon formation. So, and here you see it just straight. So that is nice. If we now come to the first test we conducted with premixed landfill gas and 30% fuel recirculation, you also see that we are in the same range, also around 0.5 watts per square centimeter. And now the last test, where we run with real landfill gas and 30% fuel recirculation, we are also in the same area, but we are a little bit lower, and that was unfortunately caused by a leakage of the cell. So it's we had during operation. And also you can see that we see a little bit higher fluctuations of the power density, and this is caused by the setup because we use a pump. So in a real system you would try to use an ejector instead to get rid of this. But in general we can say that we were able to operate successfully SOFC fueled with premixed and real landfill gas with a 30% fuel recirculation to avoid carbon formation. And yes, so that is the result. we achieved. So we went from the motivation, why we are using landfill gas in a solid oxide fuel cell, about some challenges, and we can handle those challenges by using anode fuel recirculation to avoid carbon formation. So what can we learn now from the investigation at the cell level for the system level? With this I will conclude. And there are 3 points. So first of all, we have a highly efficient transformation of landfill gas of the low heating value in a SOFC into electricity and heat, and that is landfill gas we cannot use in a combustion engine anymore. And then also anode fuel recirculation is an option to prevent carbon formation and avoid extra gas supply during operation, so simplify the system. And finally, I presented you a test conducted on Singlecell level, running for 150 hours, fueled with real landfill gas and an anode fuel recirculation of 30% to avoid carbon formation. With this, I would like to say thank you for your attention. You're very welcome to ask questions, and furthermore, if you would like to know more about DTU Energy, what we are doing, you're very welcome to visit us at booth E651. I was talking about solid oxide fuel cells. If you are more interested in this area, so also about solid oxide electrolyzer cells, Anke Hagen will give an interview in the public forum on Thursday about that at 1:20 p.m. So thank you very much.
Thank you very much. Are there any questions from the audience right now? No? Okay. So as he already mentioned, booth E65 right this way and then turn on your right side.
Yes.
If you have further questions or if you want to listen to another discussion in the public forum on Thursday. Thank you very much again.
Thank you.